My name is Peyton Holston, and this is my lab report for Physics 2211, Lab 3. The objective of this lab is to estimate the mass of a black hole using the observed motion of a star orbiting the black hole. A few of the physics principles and formulas we'll be dealing with during this lab is Newton's second law of motion and Newton's law of gravitation. These two formulas will serve as the center of our calculations during the lab. We will also be using the idea of parallel and perpendicular forces as it relates to the rotating motion of the star around the black hole. So as you can see, the total net force is composed of the parallel force and the perpendicular net force acting upon an object, as well as the total change of momentum over change in time is composed of the parallel and perpendicular components of the change of momentum. These formulas go a little bit more in depth and just show you different ways to calculate, as you can see in the first one, the change of momentum, and shows you the relationship between net force and its parallel and perpendicular components and changes in momentum. The last formula you see here is just showing that the net force acting on this lab is gravity, because we are assuming that the only force acting on the object, being the star, is the force of gravity. So here you can see the beginning of the code necessary to create this model. We had to input our email address as a seed to create the orbital path of the star. In the system properties and initial conditions section, you see where we initialize G being the gravitational constant, the mass of the star being 2 times 10 to the 30th, and delta T being 86,400 seconds, being the amount of seconds in 1 day. And we initialized our time starting at 0. This is the first section of our while loop, which we use to first calculate or to find the initial and final velocities. And knowing that, we were able to calculate the initial and final momentums by multiplying the initial velocity times the mass of the star, and the same applies to the final. Then we were able to calculate the change in velocity and the change in momentum using v final minus v initial and p final minus p initial. We were able to calculate the change in momentum over change in time by dividing delta p by delta t. And finally, since we know that delta p over delta t equals F net, we could set that equal to it, as you see on the last line. In the next section of code, you can see we're working to calculate dp dt in the parallel direction. So in order to do that, we have to get the direction, which you see in the form of p hat, and the magnitude of that vector, which you see in the form of d mag p dt. We take the magnitude of the final momentum vector minus the magnitude of the initial momentum vector and divide by the change in time. On the line after that, you see we set F net parallel equal to dp dt parallel, because those two are equivalent. And the line after that, you see we set dp dt perp equal to dp dt minus dp dt parallel, which you could see from one of the equations mentioned earlier that those have a equivalent relationship. And then we can set F net perp equal to dp dt perp, because those, as mentioned earlier, have an equivalent relationship. Then in the last section, you see we're able to get the distance of the star from the black hole using the magnitude function. Then MBH, which represents the mass of the black hole, is calculated by isolating for the mass of the black hole in the Newton's law of gravitation formula, because we have all the other components. And then the last line finally prints out that value to the console. Here you can see the GlowScript code running, the three vectors pointing in the directions of the total net force, the parallel direction of the net force, and the perpendicular direction of the net force. Here you can see that the mass of the black hole was estimated to be 1.0587 times 10 to the 34, which is within the reasonable estimate of the size of a black hole. Finally, the last questions that we're going to deal with are, how is the net force different from the rate of change of momentum? So we know mathematically that the net force and change in momentum are the same, but they represent in the real world two different phenomena, one of which being the net force, which is acting upon the object, which causes the momentum to change. Now the second question asks, if the black hole is replaced with another black hole, could you tell the difference? The answer to this is no. It would be impossible to find the mass of the new black hole, because the mass is estimated using the motion of the star, which the question stated was unchanged. Therefore, if the star's motion remains the same, then the new mass of the black hole cannot be calculated.